Hello, everybody. Hope you all are doing good. Tonight we are going to talk about biofuels. Okay, and this is one of my favorite topics because I own a farm and I always wanted to grow some biofuels. That's all part of why I bought this place. So let's talk a little bit about what biofuels are because they're very, very interesting. So in this lecture, we're going to help you understand what bioenergy is. And I say biofuels, I'll say bio this, bioenergy, all these different terms. Okay, so remember, bioenergy is a broad term, and the biofuels deals with um, what we liquids and stuff like that. So there's these terms get kind of confusing. I kind of use it interchangeably throughout this. Okay, so we'll talk about the major sources of bioenergy. We will talk about how we use bioenergies and at what levels we're actually consuming them right now. How we make the different forms of bioenergy. We're going to talk about the EROI of the different forms of energy, and also is bioenergy the future. So bioenergy is energy derived from biomass. So any living matter, all right, is considered bioenergy, and it has to be living like and recently dead, all right, because coal, remember, and oil and natural gas is just energy from was bioenergy at one time. It just stored over time for us in this nice little pocket of uh, in the earth. We can just stick a straw out and suck it out. All right. So the tough part about bioenergy, it's the same thing as coal, natural gas, and oil. It's just that we have to do it right now on top of the earth. All right, it's not stored. We have to create it on time, just in time inventory, just in time energy. All right. But biomass consists of organic material derived from living or recent living organisms and contains chemical energy. Plants took the sunlight and converted it into chemical energy and put it into their cells so that we can eat it or burn it or make it into oil or do whatever we want with it. All right. So it wasn't for that process, those primary producers, we would not have this energy to use. So we're just taking how they convert the sunlight into that chemical energy, and then we take it to the next step, and then we convert it to another type of energy that we can use and get use out of. And there's also what's called first generation biofuels and second generation biofuels. Okay, this isn't too. I hope this makes sense here. First generation is like cereals, and starches, and sugars, and oil crops. So these plants are grown primarily for the use of biofuels. All right, and this is what we've started this out with. Okay, but we've grown our process so we can use what's called second generation biofuels. We've gotten so good at getting stuff out of this stuff, we can get stuff out of the stuff that's already dead. All right, and we could use it in that, and it's already been consumed. It wasn't this stuff, this animal manure came from this biofuels first. All right, for the plants, the animals eat. So it's second generation. It's skipped another step, so it's lost a little bit of energy on the way, right? Just like that photon bouncing around in the sun loses energy and turns into well, it's not a photon, it's I don't know, it's a, what is that called? Gamma ray or whatever, a gamma ray inside the sun, and then it goes out and hits around and becomes a photon. Same thing. The sun hit this from a photon, became the chemical energies of the starches, and then the cow ate it and pooped it on out to the animal manure. And it lost a little bit of energy, a little entropy on the way, right? So bioenergy is bioenergy carbon neutral? Not really, depends. The principal energy from biomass is carbon neutral, releasing no net carbon into the atmosphere. And this can get a little bit tricky, and I don't know if you guys know the difference between carbon positive, carbon neutral, carbon negative. But what we have right now in the world, a problem with global warming is that we have carbon positive. Okay, we are taking carbon out of the ground from the fossil fuels and adding it to the carbon cycle, like we talked about way back when. All right. So this carbon cycle, there's more and more carbon dioxide out here into the atmosphere. Okay. Um, with the principle of biofuels, since this is a plant and they sequester carbon inside this tree trunk, okay, so they are taking carbon in, and when we finally burn it, we're just releasing the same carbon that was already out here in the atmosphere, put into this tree trunk, and then putting it back in. So we're not adding anything into the atmosphere when we're actually releasing this, burning this tree, or that oil in the hemp, or the oil in the algae. Okay, so we're not really adding to the atmosphere, to the carbon levels. It's a one-for-one takeaway. So that's why it's considered carbon neutral. But if it's done right, and if we pick the right crops, we can actually be carbon negative. All right. So once we actually use this, some of that carbon is actually going to stay in the soils and in the roots of these crops. So if we pick the right crops, we can actually store more carbon in the soil while staying, and then when we release it and use this as a fuel, all right, some form of energy, we were actually releasing less carbon out. So it will be carbon negative. All right. So all depending on how you do it. If you don't, grow these trees right, and you're using a lot of diesel, you're going to be carbon positive, right? So we got to do our carbon footprint for each one of these crops. That's what us ecological economists likes to do. All right. So we need to be careful. All right. And of course, this only holds true of forest, which sequesters the carbon dioxide and not cut more and used as a biomass source. So it depends on what we use the trees for and how fast we cut them. So if we put them into a home, that's going to store that carbon. That carbon's not going to be released. But if we use it to burn, then it's going to release that carbon, right? But we can also lose the tree from growing and sequestering the carbon, so we need to plant some more to replace it, right? The story of the Lorax, it's real. For more than 1 billion years in developing countries, burning biomass remains the principal energy source for heating and cooking. All right, so we still today there's over I think 1 billion people that are using wood and manure and all that other stuff. They just go out, pick up a cow patty, throw it on fire, brew them up some coffee, baby. That's what I'm talking about. All right, in developing countries, we depend on fossil fuels for most of our energy. Wood burning is still a minor heat source for some homes. All right, I almost bought a wood burning stove for my house. Right, I have a Ben Franklin one. It's been around for a long, long time. His design hasn't really changed. That thing is an engineering marvel. I have one of those down in the tack house there. The thing pumps it out. Right. In the developing countries, also burning agricultural waste and straw and corn stalks, such as reeds and elfin grass, have become adopted. And this is called cogeneration. All right, and it is one of the most fast and growing sources of new energy in the United States. Okay, and it's actually like a second generation energy source because the food and stuff, the stuff you want to throw in there to burn is actually just the agricultural waste. It's the leftovers from getting that corn. It's leftovers from getting that rice husks. So you're taking the rice husk and the corn stalks and you're throwing them in there. All right, so it's really a second generation, which is good. All right, because we're reusing it, reusing that energy. But by doing this, producing two kinds of this useful energy in the same facility, the net energy yield from a primary fuel source is increased about 35% to about 80%. So you're getting more and more. So a lot of that, the secondary waste, the secondary cogeneration, the corn stalks are, offsetting some of that waste. Okay, so you get a better efficiency. The EPA estimates that the cogeneration could produce almost 20% of the U.S. electrical use, or equivalent of about 400 coal-fired plants. So we have put in a good push for this cogeneration plants. But it's really all about location. All right, so the cogeneration biomass is energy level are very different and are restricted for where the plant can grow. Okay, as we go through this, I'm going to point that out, and I think you'll understand about this because if you're in West Virginia, you're going to have a lot more wood, right? If you're in Iowa, you're going to have a lot more corn stalks. So each one of those biomasses has a different water value and BTU. All right, so it really depends on where you're at, and to get your full source, your fuel source. But we harness bioenergy for many types of different plant matter, including wood, trees, cars, all different stuff. So we got the wood and your charcoal, manure from farm animals. I'm telling you, people actually cook with this in the third world. I mean, we did too, way back when. All right, we just pick that manure off the ground. Those cow patties could burn, baby. They got a nice little burn to them. But here and there in the United States, we also do a lot for biomass to generate the electricity, and we're just taking that crop residue, like the corn stalks or the wood chips or the rice husks or whatever, and throwing those in with co-generating for a power plant. Typically, we don't use the whole power plant as that. We tried those plants. There's a couple that say that there's sustainable wood burning electrical generating plants, but um, that's not exactly panning out the way it should be. But definitely, it does help bring down the use of the coal with a 60-40 blend, 60% coal and 40% crop residue. Because this crop residue just cannot keep up with it, too. We just don't have enough to burn for the amount of electricity that we use. It's amazing. So we need to change how we do this. We need to stop burning stuff. Period. Forest for electricity. There's better ways to generate our electricity. There definitely is. But this is just one way, and we need to transition, right? So we got to use what we have. Okay. So let's keep those coal plants alive for a little bit longer, but let's start trying to get some cogeneration going in there. Okay. Forest residue is also left over. So when Trump says he wants to rake the forest, that's what we can do. We can just rake the forest and bring it out there to the power plant, right? Um, we also use processing waste from wood mills and burned at power plants. So landfill gas is also burned at power plants. Okay, and we'll show you a schematic of how we get this landfill gas out of here. Just a methane digester underneath the ground, and we'll talk about this here later on in the PowerPoint slide. Livestock waste from meat loss turned into gas from anaerobic digesters. We'll talk about that as well. Biofuels for powering vehicles. And this is probably what the most popular thing is for a biofuel or for bioenergy. And that's why I always use biofuels as a term. I could say biogas, and it's all the same, but biofuels are for powering our vehicles. And here in the United States, we primarily grow corn for ethanol. That is because corn grows well here in the United States, not because corn's a good choice. And we'll talk about that later. But we have the biome, what's known as a biome. We've got the temperature and the precipitation to grow corn. And then if you look at Brazil, their main ethanol is sugarcane because they got the biome. They got the temperature and the precipitation to grow the sugarcane. We don't. Okay. So it really depends on your location. All right. We also use sugarcane, soybeans, rapeseed, and other crops for biodiesel. So this is a little bit different than the ethanol. This is a biodiesel, and depending on the plant and the lipid oils inside of these seeds, and that will give us the biodiesel. So you basically a vegetable oil that you put in your pan, or you fry your French fries in that vegetable oil. That is basically biodiesel. That's exactly it. You just add a couple different additives to it, and lo and behold, you can run your car on the vegetable oil in your closet. Or if you had a diesel engine, okay, you could do it in there. But the ethanol, you can drive your car on ethanol. That's for sure. Your gasoline on ethanol. Using cooking oil for biodiesel. Okay, like I just said, algae for biofuels is probably my favorite one. We'll talk about this. I think this is going to be actually the key to transferring if we're going to have any kind of biofuel future. It's going to have to be algae, in my humble opinion. Plant matter treated with enzymes to produce cellulose ethanol. So we have a new product called cellulose ethanol. So we're getting the sugars, instead of getting the sugars directly out of the corn, or the sugar beets, or the sugar cane, we are getting the sugars out of the cellulose of the plant. So the leftover residuals of the hemp plants and stuff like that. And a lot of grasses has this cellulose ethanol, cellulose in it, that we get the sugars out to get the ethanol. So most fuel wood is used widely in developing world. The most fuel wood is used widely in developing world. So the rural area, developing countries are definitely burning the wood for their major usages. Okay, that's their main biofuel. Okay, but developing countries still source bioenergy, are producing biopower to generate heat and electricity. So we're still using wood as well here in the developing world. But this is the primary use. And over 1 billion people in the developing countries who rely on wood from trees and heating. All right, and this could have some devastating effects if not done properly, with deforestation, soil erosion, and desertification. And we're seeing that starting to rear its ugly head in our face. And there's some other things like planting the trees for soybeans. Soybeans too down in Brazil. They just started doing that. But palm oil is a big thing. Their palm oil grows as the biome is nice and tropical. So a lot of the tropical islands in the Philippines and stuff like that are cutting down there. I think it's in the Philippines. You might know about this. They're cutting down the forest, putting up the palm oil, and that's really hurting the ecosystem down there. So we can generate electricity using biomass. So biopower and biomass are used to generate. And also doing is taking the waste products from logging, sawmill, paper pulps, or anywhere the second generation of these plants, of this energy from the plants, and just instead of taking it to the landfill or selling it to the coal-fired plants, all right, and they're doing what's called co-firing and co-generating. All right, it's usually typically about a 60 to 40 blend, 60% coal, 40% biofuel, but it always depends on what you're getting. If you're getting sawdust, or you're getting paper pulp, or if you're getting corn husk, or whatever it is, each one of those has a different moisture content, a different BTU, different drying time, and different drying techniques, all these different things. Okay, so it really depends on the biomass that you're using when you're co-firing for that ratio, that 60-40 ratio. It's just typical. We can also convert the bioenergy to what's called a gaseous state, called gasification, or we can do pyrolysis, produce liquid power fuel that can be burned to generate electricity. All right. And gasification, I mean, this technique has been around for a long, long, long time. All right. And all we're doing is we can take the biomass or any of the waste stream that we have, all right, but we can do it with coal and petroleum. It's the same process, all right, that we'd be doing with all this organic matter, all this biomass, because that's what coal and petroleum really are, just biomass, just a little bit older, right? We put it into the feedstock and we just gasify it. All right, so we burn it at really high heats, okay, and it turns into the gas. All right, and it comes into the steam, comes into the gas steamer. All right, so if it's the acid's added to it, goes right through, hydrogen is taken out. That hydrogen can run a fuel cell if we wanted to. All right. But then the syngas comes out after all this stuff, after the hydrogen's taken out and separated, sulfuric gas is taken out. Syngas comes out, all right? And that syngas can be used to burn directly as just like any other gas, to run a turbine, or to, go back and burn to burn some more waste if I wanted to, okay, for cogeneration, okay? It can run a steam turbine for some electricity, okay? It can boil some water for CO2 sequestration, okay? Or it can be made into this gas here, and then shipped out to make some more fuels, chemicals, or anything like that. All right, so this takes it and puts it into a gaseous state for transport, basically, and then we can use it wherever we want. All right, it's a lot easier to transfer this stuff as a gas than it is as coal, biomass, petroleum, and it makes any one of these into the same thing. Okay, because we're just going after the chemical pounds because we're actually taking out the hydrogen because all this stuff has hydrogen, all this stuff's in here. Okay, and we're just separating them all when we do that gaseous state into that syngas. All right, or we can do a pyrolysis, and all this is, and this has been around since I think the Egyptians used. I think the Egyptians invented this. Okay, I don't know. That might be. It's like same with the battery thing. So we don't know exactly, but I'm pretty sure that they did. All right. And also, we're doing it now is we're just taking the biomass, all right, and we put it into the reactor, which is just another um, heat heating vessel, all right, and we just put it on a certain rate, and it turns into a gas again. But then we quickly condense it, and when we condense it, some of the biogas will be let off, or we can use it somewhere else if we wanted to. Okay, but when we condense it quickly, it turns into that oil, right? And then we can take that oil and use that as a um, fuel in our cars. All right, and this can be done. This doesn't have to be biomass. This is what Germany was doing when they ran their war machine in coal liquefaction. All right, except that we're using current biomass instead of millions of year old coal. All right, we're just heating it up, condensing it, turning the gas, condensing it, and making it into that oil. And the process is basically the same. It's just the feedstock's a little bit different. We got to fine tune it for each one of these feedstocks. So biofuels can, and now we're talking about what we're going to run our cars on. Right. So biofuels can power vehicles. Right. And biodiesel is a fuel produced vegetable oil using cooking grease and animal fat. Biodiesel is what the diesel engine was made for. All right, the diesel engine was not made for oil. It was made for running on vegetable oil and stuff like that. I mean, that's how that guy invented it. Okay, it just we get a better bag for our buck. That oil down there is just the fine French wine, and now we got to grow it ourselves, and it takes some time. And we have to have a system for that. It's a lot easier just to go down and stick a straw in the ground, and it's already in liquid form for us. Okay, no wonder. But now we're going to have to figure out how we're going to switch that over because that's going to be running out. I think we all understand that after this class. So biodiesel has many advantages. It has less vehicle emissions. All right, so it's not as pollutant as regular diesel too, because remember that oil is wrapped around and it's got some lead in it, some Canadian in it, some all this sulfur and all this other stuff. All right, when you get that plant right off the vine, baby, there ain't there's just some hemp in that seed. You know, that's it. There's nothing that's toxins. Oh, there might be some toxins, but it's not as potent as it would be if you were just getting it right out of the ground in that pool. Um, Nearly identical fuel economy, so this can be transferred. If we switch over to a solid biofuel, we don't really need to switch over our transportation and our I don't want to say transportation, our logistics lines. So the biodiesel will go right through the pipelines like we already have. All right down to the plants that we already have. They can process it into the liquid that needs to be done, and then they already have the distribution system to get it out to all the gas stations. So we don't have to build any new gas stations either. All right, that's one of the reasons I don't like the transportation part for the solutionsproject.org. Their transportation thing talks about the hydrogen economy, and we'll talk about the hydrogen economy next. But that is changing the whole infrastructure. That's going to be tough. And I think we don't need to do that because we already have that. And I love hydrogen. I don't want to stop that technology. Believe you me, that is the best technology out there, I believe. It's just not cost prohibitive. But this is definitely, biodiesel is definitely something we can use and people can afford, and it creates a lot of jobs, man. And farmers need some help, okay? Even though we're out of farmland, okay? It's cost effective, so we get a good bang for our buck when we do this. non-toxic and biodegradable. So when we have an oil spill, it will just go down. It's not like regular gasoline where we have to add in all these additives and all this other stuff to make it into the gasoline that we have today. All right, it's basically already there for us. We add a little bit of other organic matter, methanol, and some other stuff, and it can go right on the ground, and you'll be okay. I don't think you can drink it, but you'll still be okay. But who wants to drink coconut oil anyways? It'll be nasty. Um, can be sourced from food waste, so we can actually get this out of food waste too. So we don't have to take food off the table. We can get it from the food waste. Okay. Um, there's biofuels, biodiesel, and there's also what's called ethanol. And ethanol you might have to be a little bit more familiar with. That's what we run our cars here on in the United States. We don't have too many diesel cars. Diesel is mostly over in Europe. They were really put a big push on it, but they didn't catch on here in the United States. So we use what's called gasoline. And ethanol is basically the biofuel for gasoline. Okay, it's produced by fermenting biomass. All right. And by what I mean by fermenting, we turn it into a nice French wine. I mean, we turn it into white lightning, not a fine French wine. We want white lightning. We want that grain alcohol. Basically, that's what we're looking for, right? And we just ferment it. We just stew it like we're doing, booze. And ethanol is now widely added to gasoline in the United States to reduce automobile emissions. So, and we mostly use corn here in the United States to make our ethanol. So we're going after the sugar and the corn to make that white lightning. All right. And you might see, if you ever go to the gas station next time, check out the pump, and you'll see 10% ethanol. All right. And that's what we have for standards. All over gasoline, all over, whether it's BP, Exxon, or whatever, it's always about 10% ethanol. I think the Sheets up there in Moon Township has ethanol 85, where it's 85% ethanol. All right, so you can get a stronger dose if you want, but make sure your car should be able to run on it. But if it's not made for it, I wouldn't do it because you'll void your warranty. Okay, but I bet you would run on it. If you guys ever see that show called Mythbusters, they busted the myth. They put white lightning, just the white lightning, the moonshine. I don't know if you guys ever seen the old movies where the moonshiners are out chasing the cops. They run out of gas, put the moonshine in the car, and then take off again. Well, the Mythbusters want to see if that was true. Guess what? The newer the car, the better the car ran on the moonshine, on the white lightning. All right. Now, having said that, we need to say that with a grain of salt. They only run around the track to the left, or they want a track and just going around in circles, and they only drove the car for like one tank full. Okay, so they do it for 5 years or 2 years or 1 year or even a month. So it wasn't real long. It just ran. So those guys could get away if they had to get away from the police, and that's what they were trying to prove. All right, but it does work. Okay, and also this is white lightning. So you can see the biggest ones in the world right now are the United States and Brazil. So the United States is taking off right here in 2005, and that's when we started the corn mandate, or the 10% alcohol mandate. All right, that we had to put that in our gasoline. And you can see Brazil, it's been high up here for a long, long time, and has basically ramped up a little bit more. And they use a lot of sugar cane. They went back in the 1970s, and I think about 90% of their cars in Brazil run on ethanol, sugarcane ethanol grown in Brazil. They don't even their oil is all basically exported. Okay, and some dirty stuff. That's them in Venezuela has some dirty stuff. I don't know how much oil Brazil really has, but they're getting the same stuff Venezuela is, and it's not too clean. And the rest of the world is starting to pick up here. In 2005, they started producing some more ethanol. So this is still an infant industry of being able to produce this stuff. Okay. Researchers are refining techniques to produce cellulose ethanol now. All right. So most of our ethanol we've seen before comes from the white lightning. It comes from the sugars that are in the corn and the beets and the sugar cane. All right. But now we find a process where we can take the cellulose, which is found in all plant material and has no food value. Right? There's still some sugars in that cellulose. All right. And the cellulose can produce rapidly in native plants such as switchgrass. So we can grow these perennial grasses and just mow them down the side. I did a report one time in college when I was up at WVU where I took the switchgrass. I grew switchgrass along the side of the in that strip in the highway. I estimated, gave some odd numbers like it was 12 feet apart and a strip that would go across all of the United States and all the miles that we had on the interstates. And I figured out, doing the rate of energy return and all this other stuff, we can grow enough switchgrass on a yearly basis to provide 1/4 of all the gasoline needs here in the United States. Well, actually, I think I did it with barrels of oil. And we did 19 barrels. No, I did with gasoline, yeah, 1/4 of all gasoline. So, hey, that's something. And that's our land, right? Who owns that land? I don't know. I think we do. We already cut it. Why not cut it with switchgrass? And then cut the logistics. You're right by there. Somewhere there's got to be a switchgrass conversion plant, right? I don't know. We'll see what happens. Then WVU didn't fall for it. But I thought it was a good idea. But it's just the same thing as making the cellulose. It's just the same thing as making it with the fermentation place, except they steam out the sugars. All right, and most of the other ones are grained or milled. All right, when we're going after these sugars. Okay, and it's processed to convert it to starch, the cellulose to sugars, and reduces the bacteria. We add a little bit of yeast for the fermentation, and it gets them distilled, and it basically becomes alcohol. All right. Dehydrated removes water, produces 100% 200 proof ethanol. All right, so you got some strong stuff. That's some white lightning right there. All right, and then we take it and burn it in a little piston, and we're off to the races. Okay, and that all comes from fast-growing plants. All right, and it's carbon neutral, and it just takes a lot of land mass. But we could use marginal land for a lot of this cellulose stuff. All right, so that grass, or we talk about the switchgrass, it doesn't need to be grown on productive land that we need for corn, right? So if we're taking this corn and we need that for our food, and it's only grows in good land, well, I wasted in our cars when we can grow this on marginal land, right? I always like to use, I like to switchgrass and stuff because it grows just about anywhere. But I like to say, why do you think they call weed? Because it grows everywhere, right? And hemp has excellent potential for a ethanol production, right? Both in the cellulose of the leftover stalks of the plant that's left over, all right? We take the cellulose out of the medical marijuana stuff, all right? But it can also be grown as a hemp plant where the seeds are detailed hybrids to go and produce the right amount of oil for biodiesel. So we can get the biodiesel out of the seeds, and then cellulose ethanol out of the stalks. Okay, use that whole darn plant. And then, believe it or not, hemp is one of the most carbon negative plants we have. It holds stores a lot of that carbon down in the roots and draws that carbon into the soil, making the soil alive. Okay, hemp is one of the most productive plants known to man. I'm telling you. But I don't think it's the best one for a biodiesel for running our cars. We'll talk about that in a second. Okay. So scientific estimates of the REOI of corn-based ethanol vary, but recent calculations place it about a 1 to 3 to 1 ratio. So 1 unit of energy is explained to get 1.3 units of energy of ethanol. So we get 1 and we get 1.3 energy units out. So it's really not exactly the best of the best. Okay. So here's the various ratios from 80 to 1. Okay, so ethanol's right here. All right, and it depends on what plant you're using. Oil sands, so it's already beaten oil sands. So we're already beating Canada. All right, and biodiesel is way down here. Okay, and you can see the hydropower, of course, is number 1. Okay, and when we look at the other, share oil, so we're almost, comparable with shale oil, all right? But natural oil and natural gas that we just suck out of the ground, that's like a 20-to-1 ratio. But now that we're doing fracking and things like that, that energy rate of return is going to start going down, all right? And maybe some of this stuff down here, the biodiesel, not the oil sands, but the biodiesel and the ethanol and the what else, will go up because of efficiencies or better breeds and hybridization and all that other stuff that we do to our plants to make them so much better. Each plant has a different ERI. All right, so we saw this, the bioethanol is right here and the biodiesel is right here for the ERI in general. All right, but each one has its own little thing. You see palm oil, all right, that we use a lot. Okay, you're getting about 6,000 barrels. I think this is barrels. Okay, of oil or gallons of oil per hectare. All right, and each hectare is what 2.4 American acres. Okay, and sugar canes right here to here, depending on what kind of breed. Corn. This is what we use the most here of in the United States, and it is the worst of the worst, man. I don't know what they're thinking. All right, switchgrass takes marginal land, and it's the worst of the worst of the switchgrass is right down here, and over here, it's blowing it away. 2,000, 2,500 compared to 6,500. Unbelievable. Popular type of wood. Okay, and this is a mesquites plant. This is probably one of the best grasses. Okay, it's also called elephant grass. Okay, is the nickname. If you want to Google elephant grass instead of reminding what this is, this stuff gets really tall, man. It's huge. Okay, and it grows just about everywhere. It's a perennial, one crop. I mean, it grows in 6 months. All right, so you bang, you got a crop. Okay. And then algae. This is probably my favorite. You can see algae anywhere from 10,000 to 13,000. This can even get up bigger, all right? Because this is just on the land itself, all right? And this is done in an open pond, I should say, pond algae, okay? And we're going to talk about algae here in a little bit, but I think algae is probably the best solution for our biodiesel or to run our cars on, okay? So gallons grown per acre, you can see in the United States, most of it is corn. All right, so we're growing 400 gallons per acre here in the United States. Okay, and then China also using corn, 213. But this is what they can grow. All right, this is what is available to them. All right, because of the biome, their temperature and the precipitation in China and in the United States is a lot different than it is in Brazil, where they can grow sugarcane and get the really good bang for their buck on the EROI of the sugars. Okay, that's what that plant does. Okay, it makes good ethanol for us, and they do about 585 gallons per acre. Okay, there, which is a good ratio. Okay. In India too. India has the same kind of, they have that wet tropical rainforest. Okay, all the way out here to, we start getting into palm oil. Okay, you're getting about 506 gallons per acre. Okay, soybeans, you only get about 59 gallons per acre, but here you get 5,020 gallons per acre of microalgae. All right, that is just amazing, and it goes up, right? Depends on how well you actually grow them. But you can see here also the cellulose switchgrass, you get 11,000 or 1,150, okay, for ethanol. So that's a good bang for your buck per acre. And you can use marginal land. You don't have to use great important land to grow our important crops, our best soil. Switchgrass, okay? But algae is really the best bang for our buck. All right. Here's just another comparison. If you look at the corn, cotton, soybean, mustard seed, sunflower, rapeseed, canola. I mean, there's so many different comparisons of whatever it is. And algae always comes out number one. All right. And you can see here that it's at 1,200. And this is basically done in what's called the raceway. So this is like the pond. that they're talking about right here. Okay, and the problem with this way is that you can get this is a open system, so any algae can jump in here or out of here, wherever it wants, right? And algae likes the sunlight, so it only grows about on the first top 6 inches of the water. So everything underneath this pond is all dead space. Okay, so what they've actually done is been able to increase the oil per gallon, by putting algae in basically fish tanks, and these are designed in all different ways. All right, and just a little fish tank. So now you have just the right amount of water. All right, it's tilted, so you get even more sunlight, and it's a closed system, so no new algae gets reintroduced or reintroduced. It's a closed loop system, so everything basically is recycled throughout this system. All right, and this is just one. I think one of the first ones they invented at MIT. But you'll see some more designs of these micro algae as we'll get through this presentation. Okay, see these are just like in little tubes. Okay, many of the special species of algae are now being cultivated to produce biodiesel, ethanol, or even jet fuel. Because there's like 30,000 different known species of algae or something like that, and each one has its own special lipid oil inside of it. All right, and we can target that lipid oil, and if we can grow them in a nice closed little system, all right, and keep those algae, separated and don't get them crossbred, we can make the most potent one that we can. All right, and detail each one to what it needs to be for jet fuel, for running our cars like gasoline, or making a biodiesel for our tractors. All right, so each one of these special 30,000 billion vegan algae out there, gives us a different carbon chain that we can chase after. And each one of those carbon chains are made to run our planes on. There's a special one to run our planes on, there's a special one to run our cars on, and a special one to run our trucks on, just like we do now. Okay? And it can be grown on large scale outdoor ponds or closed tanks. Okay? I like these photoreactors the best. All right? And they're just basically fish tanks. This one is just a bunch of tubes, okay, running down, okay, gravity fed, right? This one is just like some plastic sheets, like little baggies, okay, and it feeds on down, okay. And both of these are inside of a greenhouse, so we don't even have to have marginal land. We can be out in the middle of the desert, not the desert, because it may be a little too sunny. We have to be able to, keep the greenhouse from not getting too hot. All right, so it needs to be in some kind of a temperate climate, I guess. So the algae doesn't want to get too hot. We want to be able, but we can just use bad land. We can use what's called a brownfield. We can take out one of those old industrial places out there on the river and knock down that factory and put in one of these algae things. Okay, or you can get really crazy. Look at this algae bioreactor. This is all algae. So we go really crazy with this stuff. Okay, but these are the basic designs, just little tubes or the raceways. Okay, here's a couple more bags. And one of the best things about this, remember we talked about being carbon negative. Okay, algae is definitely carbon negative. Because algae will take carbon out of the atmosphere and put it right back into them, right? And so when we burn that algae or release that carbon from the lipid oils, it's just carbon neutral. No, we didn't add anything to the atmosphere. We didn't take anything from the atmosphere. But what we can do is what they have done is taken these algae bioreactors and put them right next to a coal-fired plant. And instead of sequestering the CO2, like we talked about in chapter 4, or way back when, lecture 4, instead of putting that CO2 down in the ground and say, don't come back, we actually feed it to the algae. And the algae uses it as food, right? And then it puts that CO2, that carbon, back into itself, and we take that algae out. We squeeze out the lipid oils for whatever we want, for biodiesel or whatever, and then we take that leftover stuff, we co-generate back into here. All right, one of my first papers I ever read, when I first started, this was Kadum, and he actually taught me about the 60-40 blend, and that's what he did back in the 80s. He set this kind of system up. I mean, he was like he was a pioneer, right? Thanks to Jimmy Carter grant, and then a new president came in, called Ronald Reagan, and he took those grants away, and that funding for that project went to the wayside. But it was working. It was pretty neat. And he had ponds. He didn't have these little baggies, right? He didn't have the bioreactors. He was putting right into a pond, right next to a coal fire plant. Back in the 80s, when we first started worrying about climate change, and it kind of got the brakes put on it. But it was a very interesting report. All right, so the technology's been around. We have been using this, okay? And now MIT has a nice little one. You can go on YouTube and put in Alan Alda drinks algae, and you'll get that YouTube. All right, because I don't know if you know who Alan Alda is. He was on MASH. And he's pretty famous if you saw the video. And he's out there and he actually drinks it because this is a superfood. Algae is also a superfood. All right, it's not, it's not for burning and running in our cars. This stuff is, they sell it at GNC. It's pretty penny, and it's healthy, man. It's superfood. So, so those are the basic ways we can run our cars. All right. Now, there's also a kind of bioenergy which is called methane. All right, methane from biomass is efficient and clean. Okay, so that natural gas, right? Coal's kind of like the wood chips, all right, and oil is basically from the algae and the lipid oils and all those sugars fermented. Okay, and methane is just the natural gas. Okay, and those anaerobic bacteria are still around and they still do their job and eat the poop in real time, right? Or I should say, dead organic matter in real time. Okay, so they're still around. And methane gas is the main component in natural gas. Okay, and is relatively effective and clean burning molecule which oxidizes easily, producing CO2 and HO2 water vapor. Um, and concerns about greenhouse gas may lead to further development in methane for biomass. But I really love methane digesters, and I want one for my farm. I wanted one for Robert Morris, but they didn't fall for that either. None of the colleges fall for my spiel. Someday, maybe. Um, but I always want to get one of these because all you do is you take shredded organic material, any kind of material, right? Just as long as it's organic, and you want to shred it down so the microbes can eat it. I always talk about worms a lot. Worms aren't going to eat that carrot because it's big, but once you shred it on down, those worms just eat it on down because it's bite size for them. So you got to get this organic matter and have a lot of surface mass for the microbes to do their job, and that's why we shred it and feed into what's called a slurry. All right, nice little liquid form after it's all shredded up and looking good. And we pump it into a digester, okay, that works without oxygen. So there's a bunch of anaerobic bacteria inside of here. All right, and as we feed in the organic mass, they sit there and they eat it up. All right, and when they exhale the natural gas, and it just comes right off like that. Simple as can be. All right, and this is the methane. Okay, except that the natural gas just a rock, right? And all the gas got trapped up on top of here underneath the ground. That's all. Okay. And we can burn that for whatever you want. We can run electricity. We can, cook our burgers on it. We can eat our farms on it. We can do a whole bunch of different things with it. Okay. And down here at the very bottom, guess what this is? We dig this out. It's called the sludge. But this is basically just compost. All right. It's now just dead organic matter. We can compost it a little bit further, probably. I'd advise it, not because it has bacteria in it or anything like that. It just we need to, if you really want to make it good stuff, we got to add a little bit of some other stuff, some more live stuff, and bring some more life ahead of it because most of the life is dead after this. All right, but it does attract a lot of good stuff. All right, even if you put it in there, it's going to bring your soil back to life. And then we take the top of the water. Okay, this is just all the different water. We take that, oxidize it in a pond. All right, and we take the sludge. It doesn't that was not all out of there. Take that, put that back into the digester. All right, and we just keep that cycle going. All right, and take that old water back and feed into the slurry again, blah, 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 right down there, boom, boom, it's a nice little loop. All right, little methane digester, okay? And farms and landfills use these methane digesters probably the most, okay? So I like how the farms do it. You can see the cow, they take the cow manure, all right, and here's the digester, okay? So they have all the stuff, all the cow manure, they just shred it up, put into a slurry, put into a digester, the same old thing, right? And this is that the anaerobic bacteria do the thing, and out comes the methane gas, and out comes the organic matter they put back on the farms. All right, this is what we call in ecological economy and ecological economies call ecological machine. All right, so this is a closed loop machine. We just add in one little input and let Mother Nature do all the work for us, right? And all we have to do is shred this stuff up and make Mother Nature happy, and she does all the work and puts out plenty of energy for us and organic waste. And none of this stuff, it just all gets reused, all right, back into the nature of things. All right, so most of the time farmers do this, and you can see these on horse farms and cow farms and pig farms and chicken farms. Okay, they become more and more popular. Problem is that they're just all diffused, and we're going to talk about that here in a little bit. But they're all separated, right? And we can't get one big mass. It's not like sticking a straw down in the ground and sucking out that oil or sucking out that natural gas. This is all in different little spaces, all right? So it's hard to get all that stuff into one little thing so we can get it into the pipeline, okay? Landfills also do this. So all that trash that you throw away nowadays is actually made into a landfill methane digester, okay? So if we would have left this all alone, probably in about 1,000,000 years, someone would have come back come back around and said, dug down here and found our landfills and would have been able to take out all this freaking methane, all right, that we left underneath. Okay, because this process was going to happen no matter what, because we got a lot of organic matter underneath there, and there's no oxygen down here, and those anaerobic bacteria are doing their things. Okay, but we just put in these little pipes, and we collect that methane that comes off of our landfills. Okay, and then we use that to run, electricity, or we use it for waste management. It probably does the most of this. I'm sure you guys have seen waste management trucks. They run a lot of their facilities on their landfill gas. They actually have some of their garbage trucks run on natural gas from their methane from their landfill. So, if you really want to check out a business that's really doing good at landfill gas, Waste Management would be probably my go-to business to direct you to. Just put Waste Management landfill gas in Google, and you'll find a lot of stuff. Okay, so it's just old stuff, and we just let Mother Nature do its thing. Now, one of the problems with bioenergy, and one of the reasons why it really hasn't caught on, in my humble opinion, is that we don't have the infrastructure for bioenergy. It still really needs to be built, because we gotta have all this different. Like this one is just for like a paralysis plant. I think that's what this was talking about. So we have the bio waste here, all right, and then it needs to be put into the paralysis part, all right, so it can make into oil, and then we got to get that to a centralized refining area, all right, and that centralized refinery area, you got to get it out to everybody else. Okay, so putting these small little farms together, whether this is for ethanol or for biogas or for methane or whatever, we still need to collect them all into one little centralized little refining area. And these are so spread out, and the agricultural products are so diffused, it's hard to really set this type of infrastructure up. All right, but we do have some centralized refining areas that we use for oil, and I believe that we can transfer those over efficiently if we tried hard enough. Okay, but that's probably one of the biggest things sticking back from the bioengineering is trying to build the infrastructure for distribution of it. All right, and we're kind of stuck by location. All right, location. So whatever the biome is, whatever the temperature and precipitation is of a certain area, is going to determine what crops can be grown, and what crops can be grown is going to determine our efficiency, whether that can be corn or sugar cane. All right, and then we have this corn or sugar cane. If you got corn here and sugar cane here, is the centralized refining area going to be able to handle those two different products? So maybe the distillers from each one of these got to do the job and get into one little product, and then we put it to the centralized refining area. But this logistics still needs to be set up on the big scale. All right, and I'm hoping that's going to be part of the Green New Deal. All right, hashtag Green New Deal, baby. I'm all about it. Jobs, jobs, jobs. Oh, ton of jobs. So, in conclusion, bioenergy is just current fossil fuel energy. All right, bioenergy can have a substantial impact on the carbon emissions if we do it right. Okay, it could be even carbon negative if we do it right. The usage of biofuels are endless, but limited to geographical areas. So we got to remember, we want to respect Mother Nature and understand that certain plants can only grow in certain areas, and we're going to be stuck with some of those things. Okay, so we've got to make the best of what Mother Nature's got us, but we have plenty of different biofuels that we can be using. Okay, the infrastructure is needed to get everything into processing, but our existing oil infrastructure will do just fine with a little tweaking, I believe. So we do really have the pipelines and everything we need to get everything around. We just got to kind of set up some micro processing plants to get it to the big processing plant. Then it would hit the big distribution plant that we already have set up. Okay, that's my humble opinion. And I think algae is actually going to be able to do that. Algae is going to be the go-to thing that we're going to. It's the key. All right, everybody, have a good evening. And if you have any questions, make sure you talk to me soon. And the paper is next week. Okay, so don't forget, if you got any questions on that, give me a holler on that too. All right, we'll see you guys.